So I will talk about on deploying secure computing, private intersection sum with cardinality, work by our group at Google. So I will start with secure computing for industrial solutions, why and how. So I distinguish three generations of modern cryptographic technology: symmetric cryptography from the early 70s, public key cryptography from the late 70s, and secure computation protocols from the very late 70s. The first two technologies are heavily used. The third one is a major theoretical and applied area, but what about industry usage, which is the question I ask today. So I claim secure computing is a technology for our time, and in 2012 I started to look and see that realize that the internet e-business is actually a multi-company operation. And nowadays we have other configurations where data is hosted outside its home domain. So the above, under increased privacy requirements, calls for secure computation. And the question was where to try our initial exploration and for deployment. And we deal with it in the paper, but here is some considerations. It has to be, we decided to do offline computation because offline can withstand the overhead of crypto and the delays. It has to be an essential and critical application that deserves to be noticed, to have the right impact. It has to involve data from different sources, different companies, and this sharing of this data has to have privacy and sharing restrictions. And alternatives have to be rejected by regulation, by privacy requirements, and so on. So we are left with computing it by a protocol. So here is the problem that we solve: intersection-sum with cardinality. So the setting is that we have a content provider, G. Let's say it has a list of people who viewed ads or content that he gave, and M is a merchant. It has a list of buyers, and with each buyer it has an associated spend value, and they share the common name, and the goal is to do analytics on these two lists. In particular, the goal is to find, under the privacy constraint, one, the number of common identities common to the two lists, and this is exactly intersection cardinality, and the sum of spend value associated with these common IDs, sum. So this is sum with cardinality of intersection, and of course we wanted to do it efficiently, mainly minimize communication. So this gives, this can be depicted as following. G has a vector of GIs, G1 to Gn, which are the users that viewed ads. M has the list of buyers, M1 to M sub M, and associated values with these buyers, S1 up to Sm. And we want to compute eventually the cardinality, which is G intersection M cardinality, and the intersection sum, which is the sum of the spans of elements in the cardinality, sum of the Sj, J in the cardinality. And here is the way we chose to use it based on our constraints and investigations. We wanted to use the solution based on commutative encryption. So G has small g commutative encryptor, M has small f commutative encryptor, G takes its vector G1 to Gn and applies its encryptor to it. So we get G of G1 up to G of Gn sent to M. M takes this encrypted vector and double encrypt it with F, its own encryptor, and we get Fg of G1 up to Fg of Gn, and he permutes it in a random order, send it back to G, takes its own vector M1 to MM, and encrypts it with its own encryption, commutative encryptor F, send it to G. G takes this vector singly encrypted with F, applies G to its element, and now it's get GF of MI, which equals FG of MI due to commutativity, and now it can take these two doubly encrypted set of G elements and M elements and find which elements are in common, and therefore the number of elements is exactly the size of the intersection. Note that if we didn't randomly order this doubly encrypted set, then G would have known the location of each element and knows the original element, and this would have given him the set intersection rather than the size. This permutation decoupled the location in the original vector and the location in the doubly encrypted vector. So we can, with a small modification of the protocol, get set intersection, but we are interested in size. So we compute the size. Now, this choice is based on the commutative encryption is Poly-Gell-Mann from '76. It was first used in a commutative way, doubly encrypted in Shamir 1980 protocol for equality, but we use it with ECC and with proof. And this solution has great properties: linear communication, the work is parallelized, it's scalable, and so on. Above all, it's simple to explain to stakeholders in the companies who are not cryptographers what we are doing and convince them that it's simple enough. And now we want to extend the cardinality to cardinality sum. So how is this extension goes? The first 4 steps of sending the encrypted sets, the sets and the encrypted sets back and forth is almost the same, but M, instead of sending just F of MI, also send encryption of SI, which is the spend associated with MI, with a Paillet encryption that he knows the trapdoor for. And he send it, and at the end, G can compute the intersection, can compute all the elements E of SI that associated with elements in the intersection, because the E of SI is carried over, and then he keeps all the E of SI for elements tagged in the intersection. He doesn't know the elements, but he knows they are in common. So he multiplies all of them and then picks a random R, encrypts it with the Paillet encryption, and also multiply it together, send it on step 5 to M. M has the trapdoor, decrypt it, get R, this random element, plus the sum. So he learns nothing because this is a random value. But G, who chose R, can subtract R and get the sum. So this is the way G computes the cardinality and the sum which we wanted to compute. And this solution has a lot of flexibility. We can change it a little bit, change the flows and so on. We can also apply the paradigm of taking a private set intersection and do size cardinality. And we also took this type of protocols, changed the crypto, added a lot of other stuff, and get it robustness. And this was robustness to it, and this was presented in crypto this year. So the status of it is that it works on analytics applications, on other applications. We also open sourced it, so it's used by other companies. So I want to conclude and say this shows us that customized new cryptography in the domain of secure computing, which is considered rare and academic, can be useful in industry. It can serve as theory to practice technology transfer. And if you do the right business analysis, use the right tools, and has the right performance considerations, it can lead to very useful and appreciated applications. And this is all I had to say. So thank you very much.